We start a new subject this week, which is called the Gpio. Let's go. So this week's outline is general purpose input-output. The Gpio abbreviation stands for these four words. Well, actually, we are going to learn how to make communication in and out of our microprocessor, because that's very crucial. I mean, any microprocessor that you come across in your real lives, be it a phone or your washing machine. I always give this example, which is the washing machine. You need to make some connection to the outside world. Okay, you can do calculations. You can do anything. We've seen that we can even implement trigonometric functions. Good for you. Very good. But what we want to do is we sometimes want to change the world as a result of those calculations. Imagine your washing machine makes a calculation, checks the temperature of the water and decides to increase the water flow, whatever. In the end, you'll have to do something in the real world, like increasing the water flow. Then you'll need to send a signal outside, or there's a sensor you need to read. As I said, you're reading the temperature of the water. There's a sensor. So the sensor is sensing the temperature that is a digital or an analog value. We're going to talk about those. Then it sends it back to the microprocessor. So you need to read and write to the outside world. What we have been doing so far, we were writing not in and out of the microprocessor, we were writing to the registers, or we were writing to the memory. Well, memory is also considered as an external device, yes, but it is not an external device in the sense that you do not communicate. It is like the hard disk. I always told you that the memory is like the hard disk in a microprocessor, and the registers are like the so-called memory of a desktop computer. In that analogy, well, memory, data memory, is something that belongs to us. Today, I'm going to be referring to this notation. Remember from the previous weeks, we had the very simple microprocessor architecture in which we had the clock, we had the program counter, we had the instruction memory, we had the registers, and we had the ALU. Even in this one, we didn't have any memory. Remember, this guy couldn't talk to the outside world. It was like a mental ill patient with schizophrenia, because everything happens inside it. There's no way that you can tell it out or get something from it. It's a closed system. But this is not what we want. But there will be traces that we'll have to follow when understanding GPIO. So I'll get back to this figure once in a while in this hour, whatever. So that's the topic. That was the introduction I tried to make. So we will cover the parallel ports. So the GPIO that we will learn how to interact with the outside world, we'll be using the parallel ports, not the serial ports. Wow, parallel port, serial port. I've never heard about them before. You may have not, I understand. But just to let you know, what we are doing right now is a parallel operation. Okay? Okay, it will allow us to exchange digital information with the external world. There's a link you can follow. It's Valvano's page. I always recommend you guys. This Valvano is a guy from Texas University. They have been using the same card, and there's very useful information there. So I strongly recommend you visit that website as well. Okay, but we are going to go over everything. Don't worry. Okay, so guys, remember the architecture. So there was the microprocessor, inside it, the control unit, the arithmetic logic unit, and the registers. And assume that this is 32 bits, a 32-bit microprocessor just like ours, which means we have 32 wires for many things. Remember, our memory was composed of cells, each one of them each with an address which is 32 bits. Remember this. So because the memory cells have address numbers of 32 bits, and because the arithmetic logic unit is 32-bit, this system was called 32-bit. Well, guys, at some point you might have realized that the microprocessor is telling the memory which address it should use. So for example, let me write a code to you. You remember, so I'm going to write a code. So let's say LDR R0 then SDR R1 R0 with indexed addressing. What this code do, what it did was, well, there's memory address, let's say it is, let's write that address. So let's say that this address has this location, so 20 million. Let's make R0 point to 20 million, so it's pointing to this address now. So get the value inside R1. R1 is here. There's something written inside it. Get it and write it inside. You already know this. These two lines of code do this. So at some point, this instruction must tell the microprocessor which memory location. That memory location is written inside R0, but that information must be transferred from this device to the memory. And the interface that it does is the address bus. So actually, architecturally, what happens is the address bus have the value inside R0. So in the address bus, in the 32 bits, in these 32 bits, actually, in these 32 bits, we have this value, okay, in the 32 bits. And in the data bus, we have the value inside R1, okay? That's how the memory and the control unit controls everything. That's how it happens architecturally. Why am I telling you this? It will make sense in a couple of minutes. Actually, if you remember this simple example, as you can see, this is the instruction. An instruction is written here, which is add register 0. So this is like add, the first line is like add R6 over R6, R3, R4. Very similar to our assembly language. And the code was written here. This was the machine code that corresponded to this instruction. Remember these from the previous weeks. Actually, we know that these numbers, because of the connection, indicate the addresses of the registers. So it is like these lines are the address memory that we are talking about, sorry. The address memory we're talking about. I've gone over this to make one thing clear. When we are writing things to memory and reading from memory, we are using the data bus and the address bus. So we made an introduction about the input-output ports, but we are talking about the memory. Actually, in a couple of minutes, in this hour and in the following hours, you'll realize that writing to an output port or reading from an input port, actually communicating in parallel with a device outside, architecturally has no difference than actually communicating and accessing with the memory. So they will be categorically like memory to us, but will be mapped to another address. This doesn't make sense to you right now, but it will make sense in time. Don't worry. I just want you to remember this architectural thing. Okay, let's continue. So guys, this is the output ports. Okay, so guys, this is our card. I mean, if you have it, you just checked it, I guess. If you haven't, maybe this is the first time that you're having a close look at the back side of it. This is the back side of the card. I mean, but yes, no, it's the front side of the card. I'm sorry. This is the front side because this is where you connect the device to the computer, blah, 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 blah. So actually, in our device, we have 6 separate parallel ports. I mean, in this figure, it doesn't look so. I mean, there's one input and one output port. Actually, in our device, we have 6 separate ports. So there are 6 different ports that you can communicate. And each port has 8 pins, which means these ports have 8 pins that you can communicate. You want to send 8 bits, you send to one of the ports, and you can read it from that port. These are theoretical definitions right now, but you will realize what they actually are when we go on GPIO deeper and deeper. So most of the words, almost all of them, can be accessed on board. So actually, port B's bit 1, which is here, which is this pin. So let me just indicate that pin. Actually, it is written here. Let's not select that color. It's written here. And it is this pin actually. So if you connect something to this pin, a sensor maybe, then you will be able to read it from port B's bit 1. That's why the names of the ports are already written on the device, if you haven't realized already. And what is nice about this card is you can connect anything to these ports. For example, a 1-bit sensor, a temperature sensor. When the temperature is high, it's providing 5 volts. When the temperature is low, at some value, it's providing 0 volts. When the temperature is in between values, from 0 to 5 volts. Well, that's an analog sensor that you can connect, or a digital sensor. Or you can connect a switch, like an on-off switch. When you press it, it's 5 volts. When you release it, it's 0 volts. I don't know. Or you can connect a LED, a digital LED, which means if you feed 5 volts to it, it will be on, it will be giving you light. A LED is light emitting diode, if you don't know already. It's like a lamp, but little lamp, which is called LED, different than lamp. You can connect to these, and by making this pin an input port or an output port, you can read the information of the switch, you can read the information of the sensor, or you can provide voltages there, digital or analog level voltages, and make the LED off and on. Actually, that would be the things that we will do in the examples and in the laboratory sessions. But the nice thing is you can connect them to any of the pins, but the nice thing is that I want to come, there are already connected devices on the board. And actually, let me just show you them. So this is PV1, as I showed you. There are 2 ready-to-use switches on the board, which are connected to some ports of some pins of port F. Which pins? Well, we are going to talk about them a lot. We are going to get into the details of how to initialize them on assembly, how to use them, and blah, blah. And there's also a LED, a very tiny LED. You might have realized that because it's on and off sometimes. That LED is an RGB LED. It can take any color. We are going to make experiments to make that shine with different colors, guys. So don't worry, you're going to learn. So you don't have to connect something. Why this is important? Well, this card was built for educational purposes. So for you, like you guys, you are trying to learn microprocessors and you want to learn how GPIO works. To actually implement something on GPIO, since this is input-output relation, you need to connect something to that device, like a LED, like a switch, like a sensor, as I said. These are already connected that you can do your tests. That's why this is an educational kit. And we are going to be using these switches and these LEDs to make experiments, guys. That would be very helpful. So that you don't need a separate breadboard or LEDs and connect wires and stuff. So they're already connected 2 switches and a LEDs that we are going to use, by the way. But still, there are many ports, 6 ports, each having 8 bits, many different bits. You can connect many devices. Actually, it's a very complicated device as well. I mean, this is a card for educational purposes, so you can connect LEDs and switches and at beginner's level understand what the card is all about. Plus, this is a very complicated device. You can do sound processing and blah, blah. Actually, some of your friends have been doing their senior project at 4th year on this card, and this card can do fantastic signal processing stuff as well. So it has wide range of capabilities. Okay. Any questions up to now? Anything that you don't understand? Okay. So where are they connected? I told you that we have switches and we have an RGB LED. Where are they connected? Well, let's start with the switches, guys. We have two switches, switch 1 and switch 2. As already written, the names are switch 1 and switch 2. Switch 1 and switch 2 are connected to ports of pins of port F. So port F has 8 pins. The first pin, which is called PF0, as you might have already realized in the world of embedded systems and hardware programming, numbers always starts from 0. The first pin of port F, which is PF0, switch 2 is already connected. And PF4 is already connected, guys. So if you press this switch, actually, switch 1, which is connected to PF4, in your codes, you'll be reading that information if the switch is on and off by reading port F4. How to read port F4, what to do with it, what is port F4, how can I read it, what is the instructions to read that? We'll get there. We are trying to make sense of it right now. So this first hour will be all about us trying to make a sense of the concepts that we are going to be dealing with in GPIO. Okay? And similarly, if you press switch 2 and if you don't press switch 2, or if you just want to check if switch 2, SW2, is pressed or released, well, you'll be in your codes checking the first bit PF0 of port F. And similarly, I told you we have a LED. That's an RGB LED. Let me make it very clear, guys. RGB LEDs. RGB LED. RGB is a type of LED that can give colors in a variety of different hues. And that's why, like an RGB pixel value, it has 3 pins, guys. It is first the R pin, G pin, and B pin. RGB LEDs, what I'm introducing to you right now. So if you just provide one logical 1 and 0 and 0, it will be glowing red. If this is 0, this is 1, this is 1, it will be glowing green. Or 0, 0, 1, it will be glowing blue. So these are logical values. This is a digital pin. You cannot provide 0.5 because it's either 0 or 1. Arkadaşlar derste olduğumu bilmelerine rağmen arıyorlar ve her seferinde hatırlatıyorum. Sekreter önemli şey. Dersteyim ama daha sonra değil mi? Sorry. This is a digital value. Digital value means from your electronics 2 courses and logic design, which means this is 0 volts, and this is in our system for our card 3.3 volts. So it provides different colors. Can I get some different colors in between? Yes, you can. We are not there yet. We are going to get there. Just don't worry about it right now. But this is what an RGB LED is. So an RGB LED has 3 inputs. If something has 3 input pins, I need, if I'm going to connect it to a GPIO of a card, I need 3 pins, right? Simple, I mean, nothing to worry about. And it is connected to 3 pins. Actually, this LED here is already connected on this card. There are connections if you just check them. There are, if you can see the dark red lines here, there are the connections. They are already connected to 3 pins of port F, namely PF1, PF2, and PF3. So if you provide 0 and 0 to PF3 and PF2, and 1, 3.3 volts to PF1 in your codes, this LED will be glowing red because PF1 is red, PF2 is blue, and PF3 is green. Well, how to provide these values to these pins, how to change the values of a port, how to make them digital ports, how to make them analog ports, we'll get there. Okay, we are trying to make an introduction and we are trying to prepare you for the subject. Any questions?
Hocam bir şey sorabilir miyim?
Please.
Bu PF3, PF2 onlar sadece LED yakmak için değil mi?
Well, you can connect other devices as well. But in this card, they are already connected to these devices. So this is the microprocessor. I understand your question, and it's a good question, actually. This is the microprocessor, okay? The microprocessor that we've been working on, this is this. You can take this microprocessor out, and you can make different connections to different pins. You can do that. But this is like a breadboard already prepared for you. and there are already connections on it so that you can use them. These are hardwired connections. You cannot change them. But when this microprocessor was produced, the sole purpose of these pins were not to connect these devices. Yes, I mean, regarding your question, of course we can connect other things to this microprocessor, but in this card, they are already connected because of educational purposes. I don't know if an answer to your question, maybe I didn't get your question.
Anladım hocam. Ya ben hani Uno kartıyla kıyasladım. Orada sonuçta
yes.
istediğimiz pine takabiliyoruz.
Exactly. Actually, in this one, you can also use any pin you like. But as again, for educational purposes, to some ports, some devices are already connected because there are many other pins. There are port F, port E, port D, port C. They've got many pins. And they've got many already connected other devices as well that I'm not talking about right now. But yes, I mean, for other microcontrollers like Uno or other Arduinos or some other microcontrollers like the PIC ones, if you have a port, you can connect anything you want. That's the answer.
Tamam hocam. Teşekkürler.
Okay. But these are already connected. And to understand the concept, we'll be using these already connected devices because we just don't want to bother finding a breadboard and just getting just cable and connect. We don't want to do. They're already connected, and we'll just by writing codes, we'll be able to test them. Then it will be very easy for us to understand how this works in assembly and in the microprocessor's architecture. Okay. Okay. Any other questions? Okay. So guys, when we were talking about the architecture, we have used very simple schematics like these. Schematics like this. Actually, they are very important. I mean, this is something very simple and stupid, I understand, but actually it provides a lot of information. Why? Because there's a microprocessor, the arithmetic logic unit is inside, the control unit is inside, the registers are inside, and the memory is something external I connect by connecting the address, data, and control buses, parallel lines, to it. And actually, I can connect a GPIO in a similar fashion, just like I talked about in the beginning of the lecture. You can connect an input-output port by connecting the control, data, and address buses. We're going to connect them. Actually, this input-output port, this red box over here, is a separate digital pad on the card, on this card, in this microprocessor. We don't see it, but it is like this microprocessor has some separate elements. It is like, I mean, in this part, there is the LU and the microcontroller, LU and the microcontroller, and there are digital pads as well, pad. So this is like a digital pad. So the address bus is connected to it, the address bus, the other thing. So let me draw the other buses in different colors. So the arithmetic logic unit is connected to the ports with cables, and the bus, it is an architecture like this. If you look at the architecture at the micro level, you will see this architecture. Actually, this is a very simple generalization of it. It is much more complex. And actually, for the first time, I'm going to show you the real schematics of a pad. So there's a pad, a digital designed circuitry for the port F, and it's very complicated actually. And I'm going to show you that. I've taken it from the data sheet. So actually, it is this. It is this. As you can see, in the microprocessor, for each port, I have these digital I/O pads. They have many things. So these are the pins. So there are 8 pins here. So 8 pins here, 8 pins. So these are the pins that you see on the device. So the PF1, PF2, so there are 8 pins here. And there are many registers here, guys. Registers, this is a register. So these are like registers, guys. They've got 32-bit values. So these are registers. I mean, like the register 0 or register 1 or register 2. Well, technically, yes, because register 2 is like a hotel room, which you can keep a 32-bit value inside, right? This is like it. But this is a separate physical register. and it has a purpose. These are called control registers. The other ones, do you remember? I've called them, these ones. Let me get back to the slides. These ones were scratch paper registers, because when you were trying to do operations on the arithmetic logic unit, you have used them to make operations on. Okay, these are the registers. But in this input-output port, there are little separate registers of their own, and they are here. These are called the control registers. They're also hotel rooms with hotel room numbers on their door. About the room numbers, we are going to get there. That's a complicated business. And there are values inside. So what values inside? I mean, what are the values? If I'm not going to use them for as like the scratch paper registers to make calculations on, what is the purpose of those values? To control the functions of this I/O port. For example, I've given an example, port F, one of the ports, port C, I'm going to connect a LED. So LED is an output device. You provide a value to it, you output something, which is, if something is on inside, it will glow red. If it is off, it will glow yellow. I don't know, just the opposite maybe. So it's an output device. So the pin will be providing data outside, or a switch is an input device. At the architectural level, this pad needs to know if this pad is an input or an output pin. Because shall I be providing data outside, or shall I be reading data to inside? Which one? Well, actually, there's an architectural digital design in it. You can change it. There's a switch for it. And if you change one of the pins in one of here, actually, it is the GPIO direction register. Let me find it. This is here, GPIO direction register. We're going to get into the details of these registers, don't worry. So let me get there. So if you make the first register 0, then, and if this is port F, then actually PF0 becomes an input port. So actually, by changing the values inside these registers, I can control the functions of the digital pad. What are the functions of the digital pad? There are many functions. For this purpose, in the following hours and weeks, we will be getting into the details of the datasheet, and we will understand what are the functions of the GPIO device. I'm going to stop the slide here, and I'm going to talk about something. So guys, actually, we start doing this at week 8, and the previous week I told you, week 7 was, up to week 7 was the first part of the course. We have learned how to use this device, how to program assembly. From now on, what we are going to learn is to understand any digital device connected to it. The fundamentals we learn will not change. We'll be using the same instructions to change the values, write some memory locations. The things that we learn on top of these will be learning the architecture or the usage or the functions of some device connected to it. So actually, this is the life of embedded programmers. Embedded programmers know how to program a microprocessor or a device, but they cannot know all the devices that you can connect to them. They know the fundamental procedure of assembly language and embedded programming, which is the next semester's course, EE315. When you learn this, a new device comes, you connect it to your microprocessor. So how to communicate with it? Because this GPIO, this digital pad, is an external device that is connected to the microprocessor via the address, data, and control buses. So how to learn it? There's 1,000-page data sheet. You read it. There are control registers. You change them, and you use them. Actually, we are going to, in the following weeks, we'll be doing this heavily, and you'll understand what it is. Okay, so what are we doing? We'll be adding new parts. Actually, we are going to learn some fundamental concept interrupts in the following weeks, which belongs to, which is a fundamental concept as well. But I mean, in general, you know the fundamentals, and what you will be learning from now on will be attaching new devices. Okay, so we're going to attach new devices, and we are going to attach these digital pads. As I said that, you're going to change this. You're going to change this, and you are going to change the value inside here, and it will change the function. What are the functions we are going to learn? Before getting to the functions of a GPIO, let's learn how to change a register, guys. Well, in your codes, when you want to change a register's value, there are instructions for that. Like if you want to change the scratch paper registers, you say something like this, right? Actually, this is not a valid code. This cannot be FF, so let me just change it. Let's say 00 for some reason. When you do this, this value is written to this register. But this is a scratch paper register. These control registers do not have names like these. Actually, no other register have names like these. So how to change this register? Before answering that question, how to change a memory location? First, you create a pointer to a memory location. Sorry. Then, by using str, you get the value inside, sorry, R2 and write it to R1. This was how to change a register value, and this was how to change a memory location value. What about how to change this? How to change this? In order to understand how to change it, we must understand that these control registers are memory mapped locations. Memory mapped locations. Control registers are memory mapped locations. What does this mean? Let's read the text in this slide. Each port is a pad on the board, a digital place, separate hardware instantiation of a physical block, a circuitry, okay? These pads have several specific registers for specific functions. These registers control the usage of the ports. Some registers are used to read data that is connected to the port. Some registers are used to, for example, enable that port. Some registers are designated to indicate the direction of that port, input or output, and many more functions. These registers are actually like memory locations, guys. They are mapped to certain memory addresses, which means actually just you know the memory. I mean, let's draw a part of the memory. So this is the memory. This is the data memory, right? Like the data memory. This is a cell. This data memory has this memory address. Like this data memory is that's a data memory place, right? What did this mean? Actually, when I say this address, I'm pointing to this line, right? Actually, some of these numbers, these addresses, does not indicate the data memory, but actually they indicate some places. For example, GPIO port F data register, which is 1, is indicated by this address. What does this mean? What does this mean? Let me tell you what does this mean. Imagine I have a code like this. LDR R0, which is equal to this value, this 425 3FC. And I say str R1 R0. Well, what did this operation do? Previously, you knew that this was to access the memory, right? I'm going to get the value inside R1, the scratch register, get that value, write it to a memory location, I always said. Which memory location? This guy points. Actually, because this is not mapped to the data memory, this value is not mapped to the data memory, it is mapped to this register. When you do this, because the pointer points to here, actually you are not writing to the memory, you're writing to this register. These are called memory mapped control registers. You're in your code, you're doing it like you're accessing the memory, but that part of the memory, that address, this address number, is not physically mapped to the data memory. It is mapped to the control register. That's why in the end, you're not changing a value inside the memory, you are changing a value of the control register. This is something difficult. We are going to just digest it. Any questions? Sorry. Any questions? Okay. So let's make a whiteboard presentation. So guys, imagine, let me write some codes. Let's write some codes. Okay, so very simple line of code. I'm writing this value to R0. I'm writing this value to R1. I'm using R0 and R1 in the following lines of code inside square brackets, which means R0 and R1 are, anybody would like to say what are they? Are
Address.
pointers, but good point. Yes, they are address values. That's why we call them pointers. Correct answer. So guys, they are pointers. But where are they pointing to? I mean, when I say str, it's going to take the value inside R0, write it to where R0 points. It's a pointer. Before, I always told you that they are pointing to the memory because I lied to you guys. Where they are connected to is written in the data sheet. Some address values are connected to the data memory. Okay, data memory. Data memory. Some address lines are connected to the data memory up to something like this actually. I don't exactly remember. But some of them are not. Actually, these are connected to some digital pads, guys. And actually, this is connected to one of the control registers. That's why this line of code is writing something to the memory, but this line of code is actually changing a control register value. Which control register? Well, check the data sheet and find out which control register or which port is connected to this location. Any questions? Any questions? Good. So I guess you understand. I mean, any device we want to control, they will have control functions, a function register, control registers, and we are going to map our address values to those control registers. And by changing those registers, addresses, sorry, and by changing the values, by writing to those addresses, we'll be accessing those registers and we'll be controlling the device. This is called memory mapped I/O. Okay. Okay. So if something connected to port F, actually 2 slides earlier, we said that 2 switches and an RGB layer is connected to F, then we can read and write to these devices by reading and writing to this memory location. So as if we are reading to memory, we are or writing to memory or reading from the memory, we are using this address and we are connected to this data. And actually, if you write to this address, Gpio data, which is this, you are writing the values. And by writing to this address, we'll be making the LEDs on and off. Sorry. But before being able to do this, there are many initialization steps for ports. Because ports have many functions, you have to prepare those functions. How do you do that? many function registers. First, change the control register of this guy. So make the second bit of this one. So get to the 8th bit of this guy 0. You make a procedural changes on each register. The device is set for a function because these devices can do many functions. You want to use it for some purpose, drive a LED, I don't know, which we'll be doing. This is called port initialization. And we use control registers to do a port initialization. And we are going to do it in code. Which registers, what is their memory location? What happens when I change a bit on those registers? Everything written in the datasheet. And in the following hours on Friday, we'll be referring to those lines and changing the values and stuff. And with those procedural initialization and the codes, we'll be making the LED on and off. That's what will happen. Okay, so for different purposes, ports can use various registers I said, what kind of functions can a port have? Actually, you can use this as an analog port, which means you can connect a sensor. You can analog port means you can get voltages between 0 and 3.3 volts and values in between, 1 volt, 2 volt, because a sensor could be a voltage, providing voltage value, a temperature sensor providing a voltage value, the example that I've provided in the beginning of this hour. Or you can disable an alternative function. There's something called the alternative function. We'll get there. Or digitally enable it, which means make it a digital port. Set its I/O direction. Is this an input port, output port? Enable the clock. There should be clock enabled to it. There are plop registers connected to it for some reason. We're going to talk about that. So there are many different functionalities you can change. For all those functionalities, we have many registers. We will learn how to use them in the following hour. Okay, any questions for today?
Benim yok hocam.
Tamam, çok sağ olun. Var onlar söylesin. Ya da Cuma'ya kadar sussun. Tamam o zaman. Kapatalım.